Here are the solutions to the homework assignment that goes with section 5.1. First, determine the quadrant in which the terminal side of the angle lies. To answer this problem, you need to know the four quadrants. If this is the y-axis and this is the x-axis, then this one here is quadrant 1, this is quadrant 2, this is quadrant 3, and this last one is quadrant 4, using Roman numerals to label those. Now we're going to decide in which quadrant an angle with a radian measure of pi over 5 radians lies. Let's sketch this angle on a y-axis and x-axis to see which of those four quadrants it's in. So here's the y-axis and the x-axis. The initial side starts at the origin and goes to the right along the x-axis. This angle has a positive measure. We're going to create it by rotating in a counterclockwise direction. From the lesson presentation, we know that a half circle ending up right here would be pi radians. This is a fractional amount of pi radians. This is 1/5 of pi radians. So imagine this half circle being separated into 5 equal spaced wedges. 1, 2, 3, 4, 5. Pi over 5 is one of those wedges. So approximately this direction up here. In blue ink is the acute angle that has a measure of pi over 5 radians. This angle exists in quadrant 1. Now question 1b. What about an angle whose measure is 7 pi over 5 radians? The initial side starts at the origin and goes along the x-axis. This has a positive measure, so it's created by rotating in a counterclockwise direction. A complete half circle is pi radians. 7 pi over 5 is greater than pi. 7 pi over 5 is equivalent to 5 pi over 5 plus 2 pi over 5. The 5 over 5 reduces to just pi. So if we want to visualize where this angle is, a complete half circle would be pi radians, and now we need to do an extra 2/5 pi. Imagine that the half circle continues rotating around like this, and then separating that bottom half circle into 5 equal sized wedges. 1, 2, 3, 4, and 5. 2 pi over 5 is the same as 2/5 of pi. It's 2 of those wedges. The other blue line would come down in this direction. The angle is this angle here, rotating around until you get to this side. This ray is in quadrant 3. Next, number 3a. In what quadrant is an angle with a measure of 1 radian? Let's sketch it to find out. Draw the initial side of the angle starting at the origin and tracing the x-axis to the right. However long you draw this ray is the radius of the angle. Next, we're going to rotate the end of that ray in a counterclockwise direction. If we went all the way to here, a half circle, that would be pi radians. Pi is the same thing as 3.14. So a half circle is a little bit more than 3 radians. Our angle only measures 1 radian. Imagine that the half circle is split up into 3 equal wedges, plus that little bit extra to be the 0.14. 1 radian would be one of those wedges. So we would draw the blue line coming in this direction. Another way to think of 1 radian is it's the angle that is created when the arc length is equal to the radius. The distance from the center out to here is a certain length. Let's call it r for radius. When that arc length is exactly the same length, that's 1 radian. So this acute angle measures 1 radian, and the terminal side is in quadrant 1. For question 3b, What about an angle whose measure is -2 radians? Let's sketch it to visualize. The initial side of that angle starts at the origin and goes to the right. This angle has a negative measure, so we're going to rotate in a clockwise direction. The end of the ray is rotating around like this. If it went all the way to there, that would be -pi radians, or -3.14 radians. We only have -2 radians. So let's separate our half circle into 3 equal wedges with that little bit extra, which is the 0.14. If the angle is -2 radians, we want to have 2 of those wedges, so it's this right here, which is the terminal side of the angle. This terminal side is in quadrant 3. Next, number 7a, sketch this angle in standard position. So we need the y-axis and the x-axis. The initial side of the angle starts at the origin and traces the x-axis going to the right. This angle has a positive measure. It's created by rotating in a counterclockwise direction. So take the end of this ray and rotate around in this direction. If you rotate an entire half circle, that's pi radians. Well, how does 5 pi over 4 compare to pi radians? It's greater than pi radians. 5 pi over 4 is 4 pi over 4 plus an additional pi over 4. The 4 pi over 4 is the same thing as pi radians, which is the half circle, and then we want to go an extra pi over 4. So I'm going to draw another half circle underneath, going all the way around, and then split that bottom half circle into 4 equal parts. 1, 2, 3, and 4. Pi over 4 would be one of those parts. The terminal side of the angle comes along like this. Starting here and rotating in this direction and stopping there is the 5 pi over 4 angle. Next, question 7b. Draw the angle that has a measure of 2 pi over 3 radians. So here's the y-axis and the x-axis and the initial side of the angle. This angle has a positive measure. It's created by rotating counterclockwise. I'm going to draw my half circle. That half circle is pi radians, but we only have a fractional amount of pi radians. We have 2/3 of pi radians. Let's split this half circle into thirds. Right up like this, and then maybe like this. I was trying to create 3 equal-sized wedges. 2 pi over 3 would be 2 of those wedges. So the terminal side of the angle goes up in this direction. The angle starting here, rotating until you get to there, is the 2 pi over 3 angle. Next, determine 2 coterminal angles. One of them needs to be a positive angle, the other needs to be a negative angle for the given angle, and use radians when you do this. So number 11a, we're given the angle pi over 9 radians. We want to find 2 other angles that are coterminal to that one. To find coterminal angles, you add or subtract 2 pi radians. So take pi over 9, add 2 pi to it, and write down what you get. This is equivalent to pi over 9 plus 18 pi over 9. Do you agree? 18 over 9 reduces to a 2. This makes common denominators so that we can add the fractions. 19 pi over 9. This one is a positive angle that is coterminal with the original angle. Now let's try to get a negative angle. Let's take the pi over 9 and subtract a complete revolution around the circle, which is 2 pi radians, and figure out what this makes. Well, again, this is subtraction and this is a fraction, so we need common denominators. Let's think of this as pi over 9 minus 18 pi over 9. And then subtract. Negative 17 pi over 9. And this one is a negative angle. So we can use that measurement as our negative 1. Now, number 11b, we can do in the same way. If this is the angle given to us, and we want to find another angle that starts in the same position and terminates in the same position, we can add 2 pi to this number. But because this first one's a fraction, we need to have common denominators to help us add them. So let's think of this as 4 pi over 3 plus 6 pi over 3. Do you agree that the 6 over 3 is the same thing as the 2? Now that we have common denominators, we see that it is 10 pi over 3. That is a positive number. So we can use the 10 pi over 3 as our positive angle that's coterminal with this one. We need to get a negative one. Hey, let's try subtracting 2 pi and see if that gets us a negative answer. So think of this as 4 pi over 3, subtract 6 pi over 3. This makes negative 2 pi over 3. And that is a negative angle. So we use that one as our negative answer. If our initial angle was so large that when we subtracted 2 pi from it, we still got a positive answer, that just means we need to subtract 2 pi again. If that still doesn't get us a negative answer, subtract 2 pi one more time. Eventually, you will end up with a negative angle. Next, find, if possible, the positive angle complement and the positive angle supplement of the given angle. In geometry class, you studied complementary angles and supplementary angles. Complementary angles are two angles that sum to 90 degrees. But I noticed that in number 17, our angle measures are not in degrees, they're in radians. So instead of thinking as complementary angles as two angles that sum to 90 degrees, let's think of them as two angles that sum to pi over 2 radians. Pi over 2 radians is the same thing as 90 degrees. Now in geometry class, when you learned about supplementary angles, you learned that those were two angles that summed to 180 degrees. But in pre-calculus, let's think of this as two angles that sum to pi radians, because pi radians is the same thing as 180 degrees. With these understandings, we can do number 17. Let's start by finding the complement to the given angle. A pi over 3 angle plus what makes pi over 2? Now solve for x. Pi over 2, subtract pi over 3. This involves subtracting fractions. We need to have common denominators. Let's think of this as 3 pi over 6, subtract 2 pi over 6. And we can see that the result is pi over 6 radians. An angle that measures pi over 6 radians is the complement to an angle that measures pi over 3 radians, because these two numbers add up to pi over 2 radians, which is the same thing as 90 degrees. Now let's find the supplement. Our original angle is pi over 3. Let's find some unknown angle that we could add to it to equal to pi. To solve for x, we need to use subtraction. Think of pi as being 3 pi over 3, because then we could subtract the pi over 3. And the answer is 2 pi over 3 radians. An angle that measures 2 pi over 3 radians and an angle that measures pi over 3 radians are supplementary because they add together to equal pi. Next, number 17b. Let's try to find a complement. Think about what complementary angles are. two angles that add up to pi over 2 radians. But our given angle is already greater than pi over 2 radians just by itself. So there would be no positive angle that adds to this to equal pi over 2. There is none. That's like in geometry class where you were given an angle that was more than 90 degrees to start with, and you were asked for its complement, and you had to say that there was none. Now let's find a supplement. The given angle is 3 pi over 4 radians. What angle could you add to that to equal to pi? Let's solve this for x by using subtraction. But this subtraction involves fractions. We need to have common denominators. Think of pi as being 4 pi over 4. Now you can subtract them to see that the answer is pi over 4 radians. An angle that is pi over 4 and an angle that is 3 pi over 4 are supplementary because they add together to equal pi, which is 180 degrees. Next, find the radian measure of the central angle theta of a circle with radius r that intercepts an arc of length s. We're asked to find the measure of theta. And to do it, we're given a value for r and we're given a value for s. And we use the formula on page 343, theta equals s divided by r. So for number 43, let's find theta by substituting 4 for the s and 15 for the r. And we see that the answer is 4/15. That's not reducible. You could leave it like this fraction. You could even do a decimal if you want. But theta is equal to 4/15 radians. This was a good problem because it reinforces what an angle actually is. The measure of an angle, we're using theta to represent it here, is the ratio of the intersected arc to the radius of the ray that created the angle. Number 45, same idea. Start with the formula. Theta is equal to s divided by r. Substitute 25 for s and 14.5 for r. And then take a calculator and divide this to get a decimal. The result is 1.72 radians. Next one. On the circle of radius r, find the length of the arc intercepted by central angle theta. We're asked to find the length of the arc. That's the letter S from our formula we were using in the previous problem. Do you remember what that formula is? It's theta equals S divided by R. But in this formula, theta is an angle that's measured in radians. This formula implies that you're using radians, not degrees. So if we're going to make substitutions into the formula, we can't put in 180 degrees for theta. We have to do a number that's in radians. 180 degrees is half a circle. That's pi radians. With that taken care of, we can do this problem. We're trying to find the answer for S. So let's transform the formula by multiplying the r to the other side. The formula becomes S equals r times theta. And then for r, substitute 15. And for theta, substitute pi. Not 180 degrees, but substitute pi radians. There's the answer, 15 pi. S is an arc length. The other length in the problem was measured in inches, so this one should be labeled inches. If you want, you can take your calculator and go 15 times 3.14, and that'll give you the answer as a decimal. But actually writing 15 pi is both faster and more accurate. Next, number 49. It's the same idea. To find an arc length, which is the letter S, we use the formula S equals r times theta. And make our substitutions. The radius is 6, and theta is 2 radians. Notice how it's already in radians. It's not in degrees, so the number's all ready to use. 6 times 2 is 12. The arc length is a length, and it looks like length is measured in meters, so 12 meters.